Let's continue talking about basic knowledge in grow-finish pig nutrition. Let's talk to what I call the energy issue of feedstuffs. What do I mean by that? Most, if not all of the nutrients, we can measure them very precisely using different laboratory assays. Whether we're talking about protein or amino acids, starch, sugars, fats, fatty acids, vitamins, minerals, and most other nutrients, we can take a sample, we can send it to a lab, and the lab can tell us what the value is. Furthermore, a lot of these organic macronutrients like protein, amino acids, fats, and starch, we can do fairly accurate determinations using NIR technology. The digestibility coefficients for these macronutrients cannot be estimated yet quite accurately using NIR. But what's the issue with energy in feedstuffs is that unfortunately we don't have a laboratory assay to determine the energy value of feedstuffs. We can take an ingredient, put it in a bomb calorimeter, and then burn that ingredient to obtain the gross energy value of that ingredient. But that doesn't tell us what's going to be the metabolizable or the digestible or even the net energy value of that ingredient. Based on the macronutrient analysis, we can make some estimations what the value of energy is going to be, but we don't have direct measurements. So the biggest issue that we have with energy in feedstuffs, in my opinion, is that we are unable to do accurate determinations of the different types of energy values in different ingredients. If we're talking about main ingredients, cereal grains and oils and some of the oil seeds, we can have a pretty good idea of what those values are. Is when we start venturing into alternative ingredients or ingredients where we have a little bit less knowledge or less information, where the energy values could be a little harder to understand. Furthermore, because we have batch-to-batch variation in feedstuff, and is one of the main reasons why the use of NIR is highly suggested, is to be able to control that variation. If the macronutrients are varying, the energy in those ingredients is also varying. Briefly to remind us that the gross energy is what we can determine by placing the ingredient in a bomb calorimetry. If we feed that to a pig and collect the feces and determine the energy of feces and subtract the energy of feces from the gross energy, we obtain the digestible energy. We subtract the value of energy that will be present in the urine from digestible energy, and we obtain metabolizable energy. And if we subtract the heat increment produced by the metabolism of pigs from metabolizable energy, then we are going to obtain net energy. And just to remind again that the three main sources of energy for a pig are going to be lipids, carbohydrates, and amino acids. And that's why when we use NIR technology, if we can estimate these three components plus fiber and other components of the ingredients, we can do some energy estimations, but not direct measurements. To try to have an idea of what's the energy content in a practical scenario for different feed ingredients, we can use the concept of caloric efficiency in pigs. We can do determinations of digestible, metabolizable energy on the farm without much equipment needed, but we need to know the techniques. And these studies and these procedures are very labor intensive. They involve the collection of a lot of different samples. We have to prepare those samples. If we're talking about making determinations of metabolizable energy, we need to make sure that we keep feces separated from urine, so we're going to need metabolic pens in pigs. It is possible to do, but it is cumbersome. The most important thing to notice here is if we want to do determinations for digestible or metabolizable energy, we don't need to do any surgical modifications to the pigs, which is not the case if we want to study amino acid digestibility or the digestibility of any other nutrients. So metabolizable energy, even digestible energy determinations could be performed at the farm level, but they're going to be very labor intensive, and most commercial farms are really not set up to do this, and the personnel is also not trained in these techniques. If we want to determine net energy, then here we really step up the game. And at this point in time, we really need some labor-intensive procedures. We need some highly specialized facilities with very expensive equipment, with equipment that needs a lot of training to operate that. Net energy, it's simply not feasible to do or to try to do any determinations on farm, or even most research institutes and universities cannot determine net energy. Now, caloric efficiency, it's a practical approach to estimate the energy value of an ingredient under farm conditions without using much of a specialized equipment. The most sophisticated piece of equipment that we're going to need, it's going to be a scale to weigh the pigs and to weigh the feed and the feeders to determine feed intake, as we'll see in the next few slides. The basis of the caloric efficiency is that if we have the correct energy value for a feedstuff and we vary the inclusion level of that feedstuff in a diet, and then we should have a caloric efficiency with a slope equal to 0, which basically means as we vary the inclusion level of the ingredient, the caloric efficiency will not change, and that will tell us that we have the right energy for that ingredient. If the energy value that we have is incorrect, then we're going to see that as we plot caloric efficiency, and if we basically make a graph where we put an inclusion level of the ingredient in the x-axis and caloric efficiency it's on the y-axis, and we plot a line, if the energy value is not correct, we're going to have a regression line with a slope different from 0, either positive or negative, and that basically is going to tell us that we do not have the right estimate for energy in that feed ingredient. In order to calculate caloric efficiency, the equation basically it's the daily feed intake times the diet energy level divided by the daily weight gain. Well, there's a couple of components here that we know very well. If we remember the formula for feed conversion ratio, or FCR, FCR is daily feed intake divided by daily weight gain. And we can substitute that into the previous equation and basically come up to say caloric efficiency. It's going to be equal to FCR times the diet energy level. So how do we go about it? What we want to do is we want to formulate diets with similar levels of energy. They don't have to be precisely and exactly the same, but they need to be very, very close to each other. We're going to vary the inclusion level of the test ingredient in the diet, and we're going to use a regression approach. We're going to provide these different diets that we formulated to pigs, and then the pigs are going to have free access to these diets. Because at the end, what we want to do is we want to construct a regression line. Let's remember that we need at least 3 points to construct a regression line. Otherwise, 2 points is going to give us a straight line. But 3 points, with 3 points, we can make a regression line, which basically means we need to evaluate an ingredient with at least a minimum of 3 different inclusion levels. If we can use 4 inclusion levels of the test ingredient, the more points, most likely it's going to be better. And then the inclusion of the test ingredient should be sufficiently different among themselves in order for us to measure the response. And we'll see that with more detail in the next 2 examples of caloric efficiency. I'm going to use this study conducted at Kansas State University as my first example of caloric efficiency. And then they took a certain number of pigs at a particular body weight, and they distributed to pens. Most importantly here, they tested 4 different levels of soybean meal inclusion, and we're only going to discuss about 3 of those inclusion levels in order to make the discussion a little easier. They fed the pigs for 21 days, and basically the measurements that were taken was the initial body weight of the pigs, the final body weight of the pigs, and the feed intake, which is something that we should be able to do in any commercial farm around the world with really good precision if we have accurate scales and train the farm staff to take accurate measurements of both pigs and feed intake. In this study, 3 levels of soybean meal inclusion were used: 21%, 27%, and 33%. So we can see that we have a good separation of the inclusion rates of soybean meal in these diets. As we can see here in the red font, the diets, in this case, they were formulated on a net energy value, and they are fairly close, around 2,400 kcal. As we'll see in the next example, we can do and use caloric efficiency with digestible energy, metabolizable energy, and net energy. It will work for all 3 different types of energy. We can see that in this case, we know what the soybean meal net energy value is in the first line of the table. And in this case, the authors are estimating that that value is 2,087 kcal of net energy per kilogram of soybean meal, and that is what we are going to test. We also need to know what is the net energy value of all the other ingredients that are included in the diet, and then you have here all those values, and we formulate the diets, and the only thing that will vary will be the inclusion level of soybean meal with some other minus adjustments to the diet. Here we have the ingredient composition of the test diets of 21, 27, and 33% inclusion of soybean meal. And we can see that those are the levels that change. Obviously, corn has to change appropriately because at the end, everything needs to add up to 100%. So as soybean meal inclusion increases, then corn inclusion decreases. In this case, they decide to use a distiller's grain from the same batch. They were kept constant at a 15% inclusion, so that should not be a factor in the determination of caloric efficiency. And then we have amino acids. You can see how amino acids vary quite a lot between the lowest and the highest level of soybean meal inclusion. At the lowest levels, the authors even use isoleucine and valine. And at the higher inclusion level of soybean meal, we don't need as much amino acid presence, but we want to make sure that these amino acids we are meeting the requirements, and that the minimum levels in the 21% are also present in the other diets. If we look at the calculated nutrient composition of these diets, we can see that the crude protein level varies because we're including more soybean meal, and soybean meal, it's a protein-rich ingredient. So as we increase the inclusion level of soybean meal, the level of crude protein is obviously going to increase in the diet. As I mentioned before, the net energy value, it's somewhere around the 2,400 kcal, and then we try to do the best we can to maintain those values as close as possible. And then for the amino acids and calcium and phosphorus, you can see that the values are pretty much the same, or at least we don't have any limitations in terms of nutrients, in terms of amino acids or minerals that going to interfere with the performance of the pigs. If anything, we want to make sure that we're meeting the requirements, and the amino acids are present in excess, but not too much of an excess in order to be of an issue. Well, we have formulated the diets. We go ahead, we mix the diets and provide the diets. In this case, let's remember again, these were diets that were fed for a period of 21 days. So it's a fairly short-term study. And then we have here the net energy value for each one of the 3 diets, the FCR provided by the authors, and we multiply the net energy value of each one of the test diets times the FCR to obtain the caloric efficiency for each one of the diets. And as we can see here, as we increase, soybean meal caloric efficiency goes from 3,800 down to 3,700, down to 3,600. So it appears that we have a linear reduction, but that's when we need the help of statistics to figure out if this is truly a reduction or is simply something that what we want to see. And in this particular case, indeed, what the authors found out was that there was a strong, a significant reduction in caloric efficiency as soybean meal inclusion increased in the diet. This reduction in caloric efficiency basically indicates that the inclusion of soybean meal, that we did not have the right metabolizable energy value for soybean meal. In this particular case, because the slope that we obtain is a negative slope, then the conclusion is that we are underestimating the level of metabolizable energy in soybean meal, and that value needs to be greater than what the authors assigned to it. Just to reiterate, the authors assign a value of 2,087 kcals, and then the conclusion of this study is that that value is not appropriate and that value is underestimated. Therefore, the value needs to be higher than the 2,087 kcals of net energy per kilogram of soybean meal. This is the second study that we're going to use to illustrate caloric efficiency, and this is a collaboration between China Agricultural University and the National Institute for Research in France. And in this case, we can see now that we're working with pigs that are 36 kilograms of body weight. Before, in the previous example, they use 11 kilogram body pigs. Honestly, we can use whatever size of body pigs that we want. They formulate the diets. We'll allocate the diets to different treatments. We need replications. This is a 28-day feeding study. The previous one was a 21-day feeding study. But again, the main measurements here is we're going to measure the initial body weight of the pigs, the final body weight of the pigs, and we're going to do a really good calculation and measurement of the feed intake of these animals. And the feed in the water, like in the previous study, it's offered at free choice at all times. In this particular example, the authors are looking for the caloric efficiency in two rapeseed meals, one that is expeller pressed, the other one that is solvent extracted. As we see here, we have different levels of the expellers from nothing to 10 to 20. So we have 0, 10, and 20. Those are the levels that we are going to test. And then the authors are making adjustments on both the corn and the soybean meal. And then the rest of the ingredients are adjusted appropriately so we can maintain the nutritional profile of these diets to be as similar as possible. Because we're evaluating rapeseed meal, and that's also a protein-rich diet, we can see here that as the level of rapeseed meal in the diet increases, the level of crude protein increases in the diet. Same phenomenon that we saw in the previous example with soybean meal. When we look at the energies, in this case, the authors evaluated digestible, metabolizable, and net energy. And we have the values here, and the values are for digestible energy is around 14.3 megajoules, for metabolizable energy around 13.8 megajoules, and for net energy around 10.5 megajoules per kilogram of diet. The amino acids, as you can see, the levels are fairly comparable among them, and the same is true for calcium and phosphorus. And these are for the expeller diets. If we look at the solvent extracted rapeseed meal diets, we obtain the same phenomenon. As we increase rapeseed meal in the diet, crude protein is going to go up, and then the level of energy in this case is around 14 megajoules for digestible energy, around 13 for metabolizable energy, and around 10 for net energy. And like we see, if we look at all the data together, the numbers are not necessarily exactly the same, but they're very close among themselves. The authors weighted the pigs at the beginning. At the end, they calculated weight gain, they calculated feed efficiency, they estimated the efficiency of the system. We can calculate FCR, and then we can calculate the caloric efficiency for digestible, metabolizable and net energy, and we have the values here for the basal diet and the two diets containing the expeller rapeseed meal. And then we have here the values for the solvent extracted rapeseed meal. If we look them together, and then I will drive your attention to the last column, the column that says p-value, and we see that in case that this is the p-value for the slope, and then here we're doing two slopes in one, we can see that with that p-value of 0.95 for digestible, 0.88 for metabolizable, and 0.86 for net energy, we can basically conclude that because the slope is not different from zero, that's what the p-value is telling us, that slope is not different from zero, then we can conclude that the values of digestible, metabolizable, and net energy values for the expeller rapeseed meal and the solvent extracted rapeseed meal are correct. If we look at the values of caloric efficiency over the three inclusion levels of rapeseed meal, and we try to look at them in a graphical manner, we have plotted here digestible energy, and the slope of those lines have a p-value of 0.95, which indicates that those slopes are not significantly different from zero, and therefore we assume them to be a flat line, indicating that the value of digestible energy assigned to the rapeseed meal is appropriate. The same holds true for the metabolizable energy and the net energy value that the authors use in this particular example. So this is a very practical way that can be used on a farm to estimate if we have the appropriate energy values for any particular ingredient that we want to test, and it's something that we can really do at the farm level. And I think it's something that we need to think a little bit more about. This is particularly important, like I said before, when we are talking with non-traditional ingredients, byproducts, or other ingredients for which we don't have a lot of information, or for ingredients where we do have a good amount of information, and that information also is telling us that the average energy values for these ingredients can vary quite a lot. And if we have a lot of variation, then we need to know what those values are for the particular ingredients that we're using, so we can adjust the values and make the right determination and use the right values in order to formulate appropriate diets for the pigs. We saw these pictures in the previous talk, and I want to show them again because we're still feeding pigs. Now, we are talking about here growth finishing pigs, and in these phases where the pigs are going to eat the majority of feed, here's where the biggest expense in terms of feed cost is going to occur. So it's very important that the feeders are adjusted correctly so the pig can have an appropriate amount of feed intake, but at the same time, we're trying to minimize waste. So suggestions from Kansas State tell us that we need somewhere around 50 to 60% coverage of the feeder trough. If we have too little or if we have too much coverage, that's going to be a problem. Too little in the bottom left basically means that the feeder opening is not good enough, and then we're basically feed restricting these pigs. On the bottom right, where the feeder opening is too big, then these animals are probably incurring in a lot of feed waste, which is not good for the pigs nor for the efficiency of the production system. Suggestions for feeding or feeder adjustment that comes from PIC are similar to those pictures provided by Kansas State University, and in this case we can see that there's too much feed in the trough. Here we have about a 50% coverage, similar to what's suggested by Kansas State, and this will be appropriate. And this is a picture where basically the opening of the feeder is insufficient, and the pigs don't have enough access to feed. And again, this is the phase where we need to put really close attention to how much feed we're providing to those animals, make sure that they eat enough feed, but very importantly, make sure that they don't waste feed, because again, the growth finishing period is where we're going to incur in the biggest cost of feeding these animals. I want to come back again to the issue of water and then water quality and drinkers. And the drinkers must provide good water of good quality, enough amounts, and that water, in order for the pigs to consume enough water, needs to be at an appropriate pressure. Because pigs grow and they grow fairly fast, we need to keep adjusting the height of the drinkers. And the rule of thumb is that the drinker should be at the level of the shoulder. And then we mentioned before, most drinkers can support around about 10 pigs per drinker. But please make sure that you follow the recommendations from the manufacturer or the particular drinkers that you're using. In this table, we have seen it before, and it has some suggestions here of the height at which the drinker needs to be located. Because there are different designs in drinkers, then these numbers are suggestions. Follow the recommendations from the manufacturer. And again, the best rule of thumb is that the drinker should be at the height of the shoulder of the pig. When we're talking about the minimum flow rate for growing finishing pigs, it's basically we need about a flow of about 1 liter per minute, and then we should be measuring water flow rate always, whether we're talking about weaning, grow finishing, or even gestating and lactating animals. We need to make sure that the animals are receiving a good amount of water, both in terms of quantity, and also very important that the water that the pigs drink is of the same quality that we humans will drink. Let's review some of the points that we have talked up to this point here. And then what is the most expensive component or nutrient in the diet? And then I just give you a hint of what is it going to be. And the hint is component, because the most expensive component of the diet is energy, likely followed by protein and or amino acids, and then after that is likely to be phosphorus, and that's the order. And the reason why I wanted to talk about caloric efficiency is because energy is basically the most expensive component in the diet, is the one for which we have the hardest time making determinations, and we can't send a sample of corn to the lab and ask the lab, tell me what is the metabolizable energy according to a lab procedure. That up to this point really does not exist. What is caloric efficiency? Caloric efficiency is a practical approach to estimate the energy value of different ingredients under farm conditions without the need to perform laboratory assays. What is the practical application of caloric efficiency? Well, we want to use caloric efficiency to check if we have the correct value of energy for the ingredients that we're using. If we have the wrong energy value, then our estimates of energy in the diet are going to be incorrect. Our estimates of feed intake could be also incorrect, and then the ratio of nutrients to energy are also going to be incorrect. So therefore it is critical that we have the right levels of energy. And as in the first question, energy is the most expensive component of the diet, and then we don't want to be feeding excess amount of energy at a higher feeding cost that is basically going to also give us pigs with a higher fat content probably than what we want. As I mentioned before, and to summarize here, let's remember that in terms of the digestive process, everything that is not digested and absorbed is going to be fermented. And fermentation could be good, but fermentation could be detrimental. And we've been talking a lot about protein fermentation. And once again, I want to emphasize that protein fermentation in general terms is not beneficial to the pig. When we talk about nutrient requirements, we're talking about basically the minimal amount of a nutrient that a pig needs in a period of 1 day. We want to know what those recommendations are, so we want to know what those requirements are so we can set appropriate recommendations, which are values above those requirements and those recommendation values are based on the experience of the nutritionist, and also very important, they're based on the feedback that we're obtaining from the productive system. Let's remember that nutrient requirements are also normally distributed, and though the values that we obtain are averages, and that's basically a value that is going to cover the nutrient needs of about 50% of the pigs. The other 50% of the pigs require something greater, and that's why we work again with recommendations rather than requirements. The majority of the feed will be consumed by the growth finishing pigs. So if we want to think about ways where we can save feeding costs, then this is the phase or the period of the growth of the pig where we want to make sure that we're doing everything we can in order to reduce feed costs without compromising the quality of the feed. This growth finishing period also is the period where we're going to be maximizing lean tissue deposition. Let's remember that if we are maximizing lean tissue deposition, about 80% of that lean tissue deposition is water, and that's why water is so important. That's why it's important to have water of good quality. If we're maximizing lean deposition, then we're also maximizing, very likely, the profitability of the commercial production. Finally, we talk about caloric efficiency because I think it's the best practical tool that we have available in order to determine if the energy values that we're using for the ingredients, or if the energy value that we're assigning to those ingredients to be used in the formulation, if those values are correct, or if we need to do proper adjustments, because energy will determine the feed consumption of the pigs. Energy is also the most expensive component of the diets of pigs.